Okay, so today is Equilibria, Energetics and Elements, June 2011 that we're going to go through. So let's kick off. We start off with a nice definition for lattice enthalpy. This one comes up quite a lot, it should be nice and easy for you. It's the enthalpy change that accompanies the formation of a mole of an ionic compound from its gaseous ions under standard conditions. 2 marks, not bad, is it? Right, and then we get into some hydration energy. So let's have a look at this. Why is the enthalpy change of hydration of chloride ions going to be exothermic? Well, it's because bonds are made. Bonds are made between the chloride ions and water molecules. Key thing which we talk about is you've got to be really careful with your terminology. Remember, it's the chloride ions. We'll be talking about ions because it's an ionic substance. And obviously water molecules because they are covalently bonded. Right, so we now have a go at doing a Born-Haber determining the lattice enthalpy of magnesium ions. So we've got to complete this. This one, obviously down the bottom here, is going to be Mg2 plus aqueous plus 2Cl minus aqueous. Notice the formula, so it's 2Cl minus. Doesn't really matter which order you do this in. The first one we'll say is delta H hydration of Mg2 plus. And then the second one, this one here is going to be delta H hydration of Cl minus. But notice we've got 2 of those, so that will actually be 2 times that. So we need to calculate this one here. Doesn't matter which way we do it. Let's do our circle that we've done from AS. Hopefully you can see if you've got like a big clock in. These are going clockwise, these 2 arrows are going anti-clockwise. So these 2 arrows, delta H hydration of Mg2 plus 2 delta H hydration of Cl minus must equal delta H lattice for MgCl2 plus delta H solution of MgCl2 as well. So let's bung some of those numbers in. Delta H hydration, that's what we want to find. Plus 2 times chloride. Chloride, they told me, is minus 633, which I obviously need to times by 2, and that's going to be minus, therefore, 726. That's going to equal lattice enthalpy, which is minus 2,493, and delta H solution is minus 154. If you bung all that through, obviously you're going to take that over to the other side. Delta H is going to equal delta H hydration Mg2 plus equals minus 1,921 kilojoules per mole. Right, so enthalpy change of hydration of magnesium ions is more exothermic than that of calcium ions. Why? Well, magnesium and calcium are both in group 2, so they're both going to have a plus 2, so it can't be the charge which is the issue, it's going to be the size. Mg2 plus ions are smaller than Cl2 plus ions. Therefore, Mg2 plus have a higher charge density and form stronger attractions with water. Right, time for question 2. So, nitric acid gives me the 3 stages that we make nitric acid in. In stage 2, why is the equilibrium mixture both cooled and put under pressure? Well, let's have a look at it. Why is it cooled? Well, it is an exothermic reaction. So, the reason it's going to be cooled is if it's an exothermic reaction, from Le Chatelier's principle, you know that when you cool a mixture down, the equilibrium will shift in the exothermic direction, and therefore it will shift to the right-hand side. So, first thing, exothermic reaction, therefore decreasing temp shifts equilibrium to right-hand side, and therefore I make more NO2 produced. Why is it put under pressure? Okay, I've got 3 moles of gas going to 2 moles of gas, and again from Le Chatelier's principle, you know that if you increase pressure, the equilibrium shifts to the side with fewer moles of gas, and therefore more NO2 is produced. So by doing that, we increase our yield of NO2. Right, in the next question, down here, but it's useful to have this up, it says construct an equation for the reaction in stage 1. So let's have a look. Stage 1, ammonia is heated with oxygen to form nitrogen monoxide. Okay, and I've got hydrogen still around here, so I'm likely to also make some water. Okay, I now need to balance this. Right, so nitrogen's oxidation state there is -3, and there is +2. So I've had a change there of +5. Oxygen to there or to there is a change of 0 to -2. But I've got 2 of them. So overall, the change is -4. Obviously, these 2 numbers have to be the same. The easiest way to do that is to times this one by 4, which gives you 20, and times this one by 5, which gives you 20 as well, -20. So, let's do that. That's a 4 there. That becomes a 4 there. This is a 5 here. You've got to be careful here because it splits. I've already got 4 there, so I need 6 there. Let's just double check. My hydrogen's 12 there, and 4 3s are 12 there. So that's okay for that one. For stage 3, nitrogen dioxide is reacted with water to form nitric acid and nitrous acid. Well, I'm obviously going to need 2 of those there to get it to work, because I've got 2 nitrogens, and I think that probably works out just doing that. Right, so now for to actually calculate something in terms of this equilibrium. Write an expression for Kc, first of all. So if we go back to the equation, let's write it out here. like so, because we may need that later. Kc is going to equal the concentration of your products divided by the concentration of your reactants, remembering to put the two squares in there. Now, let's go back to this. At equilibrium, they told me I mixed 0.80 moles of that and 0.70 moles of that and none of that. And at equilibrium, sorry, initially, that's what I put in. So those are my initial moles. And at equilibrium, it tells me that 75% of my NO has dissociated. So, if we do 75% of 0.8, we get 0.6. So 0.6 moles has dissociated, which means I'm left with 0.20 moles. For every 2 of those, only 1 of those reacts, so that's 0.3 moles, so I must be left with 0.40 moles. And over this side, for every 2 of those, I make 2 of those, so I must have made 0.600 moles of that. Now let's work out my concentration. The concentration is in a container of 2 decimeters cubed. So you need to divide each of these by 2, which gives you 0.10, 0.20, and 0.30. So those are your concentrations. And then you pop them into Kc. So 0.3 squared divided by 0.1 squared times 0.2. That equals 0.09 divided by 2 times 10 to the minus 3, which should give you 45. For units, it's moles per decimeter cubed squared divided by moles per decimeter cubed. So that goes, so I'm left with moles to the minus 1 decimeters cubed.